Okay, everyone, thank you very much. Thank you for your patience for this initial setup here, and welcome to this talk about removing security roadblocks to IoT deployment success. My name is Eustace Asangawa. I'm Security Program Manager for the Azure IoT Platform team, and I'll be co-presenting with Thorsten Stein. Want to introduce yourself?
I'm a Senior Program Manager on the Windows IoT team, responsible there for cybersecurity, and I will share this talk together with Eustace.
Awesome, awesome. So thank you for being here. We are very happy to have you here. Throughout this talk, hopefully the message that we can convey to you is that Microsoft is leading the charge on securing IoT around the world. And that in order to get to deployment success, there are certain roadblocks that get in the way, some that Microsoft can solve, some that the community needs to come together and solve together. And what we hope to show by the end of the presentation is what Microsoft is doing in order to remove the roadblocks. So to start out, we all know in order to secure IoT, security has to go it has to be end-to-end. From devices, the connectivity, and all the way to the cloud. So I'll start with the simplest portion, the connectivity portion. On the connectivity, the industry is very comfortable with what it takes to secure a connection from one endpoint to another. The standards that govern this communication, secured communication, TLS, using identities based on X.509 certificates, they have been around for a long time. So we will not be spending a lot of time on the connectivity portion, but the message to you is that every connection to Azure IoT is done through a secure connection using these standards. On the cloud side, Microsoft has done and is doing a lot of investment, because that is where Microsoft can really lead the charge and make decisions in securing the cloud. There are many ways in securing the clouds, and there are many ways of measuring this. One of the few ways that I want to share with you is through compliance certifications. So if you look at compliance certifications, the diligence that it takes in order to maintain a secure cloud, Microsoft has one of the most expansive compliance for any cloud provider in the world. Okay? This is saying that to Microsoft, security is not an afterthought. They design for it from the ground up. They put in the diligence that is needed in order to get a secure cloud infrastructure. And it's not just the compliance. Let's look at what the public sees about that. So more than 90% of Fortune 500 use Azure IoT Cloud. We see that as an endorsement onto the work that Microsoft is doing towards the cloud. So with that, I hope you can trust us or trust the Fortune 500s that Microsoft is doing what it's needed in order to secure the cloud. So now that leaves devices, and that is where we all come in, because all of us have choices to make there. What device do we want to use in order to secure IoT? What steps do we want to take in order to make sure that the devices are deployed and operating securely? So for that, that is something that Microsoft cannot do alone, because there are other inputs to that equation, like cost, like diligence, like operational details that has to come from the deployment, the people doing the deployment on there. But what Microsoft has done in this area is gathered its experience over so many years and done research to find out what makes a secure device. And these are published under the 7 properties of highly secure devices. So these are measurable properties that you need to have in IoT devices in order to have confidence that the device will hold up its own end in security. So when you look across these properties, there are properties that are very hardware-centric and hardware-dependent. There are properties that are software. And then there are aspects of it that is operationally, like renewable security on there. One way to condense these 3 aspects is to look at security as this amalgamation of a root of trust in hardware, having the right integrity in the operating platform, the operating system, and the software that runs on it, and also cloud services. So these are things that needs to happen in order to have a secure device. So what is Microsoft doing in order to help out with this? Starting with the root of trust, going the other direction. Starting with the root of trust, embedding trust in hardware requires a special kind of silicon hardware. Just any hardware will not be able to hold up if somebody were attacking the device to get information out of it. So we refer to this as secure silicon. Sometimes some people call it hardware secure modules. And this comes from silicon providers, semiconductor manufacturers. It takes special processes to manufacture silicon that can withstand an attack coming from somebody. Okay? So Microsoft is working with silicon providers in order to enable the use of their products onto the Microsoft cloud securely. And Microsoft is working with standards. There are standards out there that define how some of these secure silicon work in order to make sure that those standards operate with the Microsoft cloud. And then you have the software aspects. Touching the metal, touching the device is a software set that Microsoft defines in the form of Azure IoT SDKs. We build these SDKs to be usable by everybody. And how can we do that? We provide a lot of choices and flexibility on there. So you have a choice of language. The SDK is offered in several languages. We don't tell you what operating system to use. You choose what operating system you want to use. And then we have an hardware abstraction layer on the SDK. So this is the way that you can layer on any of the secure silicon that is coming from the secure silicon vendors. And most of all, you have the renewable aspects of the security built into the SDK. So it will assist in updates, in renewal, in certificate renewal on the system. So we put a lot of engineering into these SDKs in order for it to deliver quality, in order for it to make sure that your security story, it continues to hold up through updates and renewals. And then finally, you have the renewable aspects of the security, which is services that over time, when you deploy your devices, you can use these services in order to update your security story on them. So on Azure Cloud, one of the main ingress points of information to Azure is Azure IoT Hub. And this comes with security controls on there. You have services on there for IoT, like device management, device provisioning service. And Windows, as an operating system, did not start with IoT. It started with enterprise. So over 20 years, there is a lot of experience from the Windows operating system and operating platform on how to operate enterprise networks securely. And all of that information is built into securing IoT today. So let's see how IoT Hub offers security controls in order to protect, help enhance the security of devices on there. So to reiterate this point, a device connecting to Azure IoT Hub, they use different communication protocols, but one thing is for sure, it is secure. That communication is secured through TLS authentication and encryption. So IoT Hub is the main ingestion point on Azure IoT. And IoT Hub has certain components that is there to assist with device security. One of it is device registry. So the model that IoT Hub works with is that for every device that connects on there, it needs to know beforehand that that device is going to connect. Why is this important? When you build your IoT and you're doing a pilot, you're working with single devices or a few hundreds of devices. When you go into manufacturing, into production, you're working with millions of devices. So sometimes you engage supply chain partners to do this. Many partners are honest, but some partners, sometimes they over-manufacture and they may side channel devices through other channels. In other words, they do unauthorized manufacturing. If you do not have controls, a way to account inside of the cloud, then devices that were not authorized to be manufactured, they get manufactured by the right manufacturers that you sanction. When they attach to the cloud, you will have no way of doing that kind of accounting. So Azure IoT Hub needs to have knowledge of what devices are going to connect, and that is done through device registry. Now, when the devices connect, there are two other questions that need to be answered. You need to know that it is the device that was meant to connect. That is attestation. You attest that this is the right device that connects. And when the device is connecting, you need to authenticate to know that it is the actual device that is connecting. So knowing that a device is going to connect is a different question to knowing that it is the device that is actually connecting. So authentication, the device that is actually connecting, and then attestation. We have three methods or three ways to do authentication on Azure IoT Hub. The first one is based on shared secrets, shared access secrets. So when you create a device registry, you can share a secret for the device that is known to the hub. And based on that secret, you can generate tokens that Azure IoT Hub can then use to trust the device, to know that it is a device, that access to that token is coming from the device. So what does that mean? On the device side, you need to protect the key that is generating that token. And that is where that secure silicon comes into place. The second method of authentication is using certificates. So certificate-based authentication. And for this particular one, the attestation mechanism is certificate thumbprints. So for this case, this is saying that if you have devices that have certificate identity on them, no matter how they got there, you can harvest this identity, generate that thumbprint, and pre-register this thumbprint in device registry. Then the thumbprints are going to be used in order to attest to the devices. So a certificate thumbprint is a digital or cryptographic summary of the certificate identity itself, small enough to uniquely identify that identity. So between the SAS method and certificate thumbprint, you see that for every device, an attestation piece needs to be registered in the cloud. This is great for brownfield deployments, where you already have deployments out there. You just need to update them to join the cloud. This is a wonderful story for that. And this is great for constrained devices. So some devices may not be able to do certificate processing, but they may have a small memory-like tamper-resistant silicon that can protect the key. So with that, you can use SAS token authentication. But the burden of registering each and every attestation piece for each of those devices, it might become a burden in the supply chain, especially if the supply chain involves many partners, where you have to transition devices from one partner to the other. Managing these secrets along the line becomes a difficulty. And that is where we introduce a certificate-based authentication. So certificate authority-based attestation. So this is still mutual authentication based on certificates, but the attestation mechanism is based on a certificate authority. So what this means is when you work with a manufacturing partner, you go through a one-time process, authorize them to manufacture the device, sign them into a trusted chain of certificates. So however many devices that they manufacture, that one authority certificate is going to be sufficient to attest to all of those devices. And when a device is connected to Azure IoT Hub, it goes through the normal TLS mutual authentication, normal TLS-based mutual authentication to attest on there. So that's authentication and device attestation. The next value that Azure IoT Hub offers is access controls onto the device. So the device has attached, is communicating well, but will give you power as the owner of the Azure IoT Hub to define what that device can do once it connects. So you can give it permission based on, you can give it permissions on what it can do, like what kinds of information it can send. You can give permission based on role, whether it's through a service connection or an Azure IoT Hub owner. You can give permission at device granular level, so per device permissions or permissions based on group of devices. And we build for scale. So for all of these procedures, when you are evaluating Azure device connectivity on Azure platform, typically you go through a GUI process. But in manufacturing, we have automated process in order to facilitate this, to make it go, to make it scale. The second, another component of Azure IoT Hub is the device twin, under the concept of a device twin. And we will see how device twin is used with device management and deliver security story. So device twin by itself offers other facilities, but for securities, let's see what it does. So for a normal IoT device, this is the operation that we expect. A device with, like a sensor, will collect information and send it to the cloud. The cloud may send some commands to the device. Now, for security, some of these commands may mean update your certificate or update your firmware version. One reality about IoT is that the device may not always connect. So when that commands come for it to update its firmware, if the device is not connected, when it finally connects, what happens? Does it continue to operate in the old stale state that we know is not secure? What happens there? And that is where device twins comes into place. So for every single device, there is a digital representation of it in the cloud inside of Azure IoT Hub. And inside that digital representation are properties that capture all the different properties in the device itself. So there are some actions that goes with it. You have a desired state of the device, which means in its properties, you put in the desired state that you want for the device. I want you to use this version of firmware, for example. That way, if the device were off cloud, when it does come back, Azure IoT Hub would ask for its reported state. What is your state right now? That's the first thing that happens. And if the desired state mismatches the reported state, then that is an opportunity for the device to update its state before any additional transactions on there. And of course, building for scale, you can batch this operation, you can tag operations based on whatever characteristics that you want on there. And you do not lose the ability to have a back and forth communication with the device. So direct methods on there. The other aspect or the other service on Azure IoT Hub is device provisioning service. So the device provisioning service, if you look at it as a service itself, it delivers a lot of convenience. When you deploy IoT at scale, you end up deploying across different geographies. You end up deploying you end up having deployment scenarios where devices may be changing custody, may be changing ownership. How do you manage all of that? How do you manage policies across all the different changes, across all the different deployments? One thing is for sure, if you did that manually, mistakes are bound to happen. And sometimes those mistakes are security mistakes. They are security oversights. So one of the security values of device provisioning service is that it automates. It automates device provisioning. That way, you can, at a central point, define all the policies that you need, and the policies get applied directly, each time the device applied for the deployment, throughout the deployment. Device provisioning service, by the way, it's also built to encourage use of secure silicon on there. Again, that is part of making sure that everybody has the right information in order to securely build devices to connect to Azure IoT. So to summarize this first part over here, what we have are a series of choices. For root of trust hardware, we do not tell you to go to this manufacturer and get this root of trust hardware. We do not tell you that this is the kind of hardware you must use. We leave the choices to you. Because sometimes security is a balancing act. How much do I want to spend and how much security is enough? We're going to talk a little bit more about that later on. So we want to allow you with those choices on there. So choices of secure hardware. We provide a very flexible SDK, flexibility to allow you to develop in the kind of language that you have, to use any operating system and not tied to just one operating system, to be able to talk to the root of trust hardware that you are using on there. And this will assist with your security renewal, whether be it certificate updates. Then, of course, we talked about the Azure IoT Hub security controls. Now, these choices, they are great. They empower. But at sometimes, or depending on scenarios, people may say, just tell me the one thing to do, or just tell me to go here. I don't want to make these choices. If you are one of those people, then the great news is we have a story for that too in Azure Sphere. It's a first-party story from silicon through the operating systems all the way to cloud. This is a very exciting story for us. And there is a talk coming this afternoon in room 612, and I really encourage you to go there and see about that. So we will not be talking much about that because there's a whole session on Azure Sphere this afternoon. One of the big themes in this year's build is the intelligent edge. If you go into the expo area, you see a lot of demos about the intelligent edge. And one of the realizations of the intelligent edge is Azure IoT Edge. Okay, let's talk about how we went about securing Azure IoT Edge. Before securing anything, you need to know what threats you are dealing with. As a connected device, as any IoT device, it is vulnerable to all the threats in IoT, network intrusion and all of that. But being an edge device, it is particularly susceptible to physical access. So this is a device, intelligent edge, meaning it's running cloud workloads. Those workloads are no longer running in a data center that is protected there. It is running in some physical device that may be in a location that is not physically monitored on there. So physical threat is one big threat. Threat of physical access by a bad actor is one big threat to the intelligent edge. And also, knowledge on how to get into these devices is very common in the industry. So we are coming into a new age of the intelligent edge, but the knowledge to analyze these devices have been around for a very long time, thanks to fields like failure analysis. When a device fails, when a silicon device fails, there is this field of failure analysis to go in there and find out what happened to those devices. You have litigation where companies sue each other and say, hey, you used my circuit, so, patent infringement and all of that. When those kinds of accusations happen, the lawyers, they have to engage a lab to go in and study to see if you actually utilize that circuit. Again, you have labs set up to do those kinds of investigations. The knowledge that it takes to do that is a knowledge that provides visibility into any silicon device. And that knowledge becomes a threat nowadays because those labs can repurpose that knowledge and use it to attack a device, okay? And then you have another threat that is coming from all the choices that we offer. So choices are good, they empower you. But the thing about choices is that when you finally deploy, you have devices you have a fleet of devices that are made up of different hardware that is running different operating systems on there that were built using different languages that are using security protocols that may not be common across the fleet. So if you bought your silicon from one silicon vendor, they may have a good story on how you do a secure boot. That secure boot story would not be the same as a secure boot story from another silicon vendor, even though they both do the job and they do it very well. From an operations point of view, those are the kinds of differences that allows for oversight. So if you're managing a fleet of devices that have those kinds of heterogeneity, they'll give opportunities for you to miss things, to miss steps on there. So how do we go about addressing this? For the physical access, the threat from physical access, we just need to be more assertive as to what security should be, okay? And then for the threat of the many choices, the changes, the heterogeneous nature of the IoT platform, we need uniformity of some sort on there. So before we go into a little bit further into talking about how we address that, let's see why Azure IoT Edge is special in this particular case, or why we should pay much attention to it. So our normal IoT patterns, you sends information to the cloud, and then the cloud processes it, and then sends actions back to the device to act on. With Azure IoT Edge, you are moving cloud workloads to the devices. Great story for distributed computing. But as the owner of those assets, you are thinking IP. Maybe some of those assets, you don't just want anybody to get a hold of it. You want to protect it. You want to keep it safe. It's a lot of IP that normally used to be protected in data centers, well-protected areas. They are now moving to an edge device that may be in the wrong hands. So that is one big reason. Secondly, with intelligence at the edge, you enable additional operations on there. Some of it may be metering. Like if you are using my module that I deploy, you need to pay on a use basis. If you use it so much, you pay so much on it. So you have metering and monetization at the edge. Because of all of that, that makes the edge device a gold mine to a would-be attacker. Why? They can invest a lot more money and know that they can get a good value, a good return of investment from that. So that is why there is a lot of motivation. That is why the edge is very attractive to an attacker, and we are strongly motivated to make sure that as a community, we can protect this. How do we go about protecting this? These are some of the principles that we are following. First, root trust in secure hardware. From that, we build integrity into the operating environment through secure boots and secure updates. And then we have a sense of a secure operating section of the operating platform. Earlier in the 7 properties, one of them was a small trusted computing base. We need to have that, a small area that you can trust exclusively and use it to protect the rest of the platform. And then you have the general computing that Edge is going to work on. So Satya announced Intelligent Edge last build, and at this build, if you go into the expo area, you see a lot of our partners. They're already showcasing solutions on the Intelligent Edge. What does that mean? That means Edge has to be secure starting today. It means we cannot wait, the world cannot wait to come up with a standard of one hardware that runs the Intelligent Edge, agree on one operating system. We know how, if anybody has sat in the standards body, you know how it's difficult to come to an agreement, and agree on one procedure, agree on one language. God forbid that's C or whatever, or language that is out there. So to solve this problem, the way we are going about it is to define what we call the IoT Edge Security Manager as a normalization layer on top of all the different hardware and all the different heterogeneous sections. We depend on our silicon partners in order to utilize, in order to implement how their silicon devices are best utilized by the security manager. And then the security manager is then going to take care of protecting the operating platform, the operating system, and the operating environment completely. So again, you see the earlier principles is OS agnostic. Microsoft is driving the charge to develop the IoT Edge Security Manager on there, and that is going to be open source. For security, it has to be that for transparency. They will define the concept of device security promises on there. So Azure IoT Edge is designed to be secure, meaning that if you contain the device, if you do not lose the device, if the device is in the hands of good actors, it's taking care of all the security that you gain from a data center for network operations and all of that. It's designed to be secure from the ground up, okay? The problem, the place we start running into problems is what happens if this device gets into the wrong hands. Because when it gets into the wrong hands, they have more tools, they have more laboratories, they have more invasive way of attacking these devices. So we define security promises in order to give a way to identify different devices and identify the different kinds of risk depending on the device that you are working with. So we have a standard promise. This means you choose to deploy. Remember, we give you a lot of choice. You choose to deploy on devices that do not have a secure silicon to protect the environment. So on there, your keys may be in a file system somewhere. If you contain the device very well, if you keep it in a secure perimeter, you would have a well-functioning edge device. But as long as one of your operators or a malactor gets in contact with the device, there is no way of telling if that is still secured. And then we have the secure element promise. The secure element promise says the device is going to take additional steps to protect the keys inside of it. So if your security operations are simple, like doing authentication, which is based just on keys, you're just authenticating. You want to know from a remote end if you are talking to the right device. A secure element would protect the confidentiality of the keys and the use of those keys to make sure that you achieve authentication. Okay. And then you have the secure enclave promise. The secure enclave promise protects both the keys and also an execution environment. It offers a trusted execution environment. So what a device cannot achieve with a secure element promise but can achieve in a secure enclave is you have executions like You have execution like monetization, metering, policies enforcement. If you want the device to enforce policies, if the device is operating in an environment that somebody can attack the execution environment, then it will be less trustworthy. But being able to protect the execution environment is one promise on there. Why do we define this different promise? Because the secure silicon necessary to protect all of those come at different cost points, and people are going to be making decisions based on the cost of that. So secure enclave typically is 10 times to 50 times more expensive than a secure element, and a secure element, of course, is different from the standard, which is considered free, although in the long run, it's not free when you consider your risks. So we're going to be certifying device. We are defining a certification plan on this. So Azure IoT Edge is going to be certified, and there is a big umbrella of certifications that goes with it. But underneath this umbrella, there is specific tenets for security certifications. Inside of these security certifications, we see that we have different lines for certifying standard devices, secure elements, and secure enclave on them. And we have a way to score it. So from level 1 to level 4, level 1 being the least diligence in security, and level 4 means the most stringent diligence in security, in device security. So why do we do this? In order to enable communications. So if you are the person who wants to deploy a device or have a deployment that have secure devices, you need to be able to find those devices. Not just depend on the vendor's claim that this device is secure. You need to be able to find it. So it is to enable communications. And we are planning to have it administered by third parties for third-party labs for transparency on them. So the way to gauge how secure, we are going to work on open standards. Open standards already exist for devices themselves. So we're going to be depending on certifications like FIPS, which measures how difficult it is to get information out of a device, how difficult it is to tamper a device. Then you have another open standard called common criteria, which validates that you have done things the way it was prescribed. So common criteria allows for a prescription on how the device is supposed to be implemented and a measure on how well you've done that. And we are also going to be instituting certificate-based device attestation. So device promise attestation. What that means is when the independent lab, when they finish testing the device and they say, yes, you achieve enclave promise, or yes, you achieve element promise, it's going to be a sticker on the device, but it's also going to be a signed attestation based on a certificate that can be verified. And let's see how that can become useful. So we give a few examples given different roles in IoT. One is the OEM, the manufacturer of a device. Now they have an ability to make an informed and optimal decision. I'm deciding to invest this much money to build this device so that I can get these devices into these kinds of markets. Is it just a simple IoT device, or do I want my device to participate in this ecosystem of rich, intelligent edge, monetization, and all of that? They can make that decision consciously. You have system integrators who have an understanding of what deployment they are working with, and they can optimize their cost decisions. So depending on the deployment, they can choose what kind of devices that they want to do there, that they want to deploy based on their knowledge of the risks that they're dealing with. And then you have the operator who can do optimal risk management. So if you look at both extremes, if you have a standard promise device that does not have a secure chip in it to protect the identities and other sensitive information on there, that means you have to trust whoever is touching that device. That means you need to put additional security controls in order to enable that trust on there. So to them, it's a balancing act. Should I invest more on device, or should I invest more on access controls? So it gives them that decision. And finally, to the developer, especially module developers in Edge, that are going to be developing modules that go into module marketplace. It gives you a lot of communication and a lot of power on what you can do there. So the module developer does not make any decisions on what the devices are going to be, but these are the kinds of decisions that they can make. My module that I've developed, it has a lot of IP that I want it to be protected. I'm going to deploy this module, and I want it to only run on devices that meet this level of promise on there. What are some of those things that might be interested to them? Maybe they have a licensing model that requires them to tie, execution on certain number of devices. If they choose a secure element promise, then they know that they can control how those devices are going to be, which devices the module is going to be deployed on. And how will they know that? They will use the signed attestation. So remotely and programmatically, they can query and see from the device whether is it a secure element device or a secure enclave device in order to do that. And that goes with when they want to protect their IP. They know that, okay, in this particular case, secure element may tell me that these are the devices running, but I do need that enclave in order to protect the IP itself in there. So it gives them that decision on them. So these promises, we have worked with partners in order to deliver them. So we have a proof of concepts out there and devices that you can go. There are video links that you can actually see them in action. You can buy the devices from our partners, and you can experience it. So this is the secure enclave, the most difficult, the most stringent. We have examples on it. And coming up, Thorsten is going to give a real-life use case study on how you can do protection from end to end for an enclave, like the most stringent security promise on here. Thorsten?
Thank you, Justus. Hello, can you hear me? Oh, no, it's up. Thank you. So before diving into this and showing you how we address this, I want to talk about the trusted cyber physical systems. How do we protect critical infrastructure? Microsoft has a lot of assets there in infrastructure all around the world. And I want to set a little bit the stage, what we're talking about and why we are doing this here. This is an article that came out in, I believe, December, January timeframe, not so long ago, about a cyber attack against a petrochemical plant, I believe in Saudi Arabia. And so that's something that we're looking into. How can we mitigate attacks against such infrastructure to reduce the risk there? So let's just have a look at what was actually communicated in the article. So just the text bites out of the article there. So what happened was that the hackers infiltrated a critical safety system in this factory. They were able to control the factory in a secure manner, let me say it this way. They were not able to basically breach critical systems there. The attack was a sophisticated attack, long planned, trident that took over control over critical systems there and took over control over workstation that allowed the attacker to control the factory. In the next step, they actually tried to reprogram the safety systems itself. That would allow the attacker actually to bring the factory in a state that allows him to cause physical harm or physical damage to the system itself. That's actually when the attack was discovered. It was discovered that the attack already took place a couple of months ago. And looking at the attack, because the attacker had already control over the factory, it is assumed that because they actually tried to cause physical harm to the factory, they might even also include a state-sponsored attack there. So with TCPS, or Trusted Cyber Physical Systems, we're looking into how can we mitigate such attacks. So the first objective is, or the main objectives that we have with TCPS is, we want to give the owner-operator full control over their critical systems. So normally when you think about cyber attacks, you look at the normal malware which is out there, but there are additional attacks we have to pay attention to. And this is what we call rogue third-party administrator. So any entity who has access to the system, could be a cloud operator, a system integrator who provides the systems for the manufacturer or for the plant operator. Those are all entities who may have administrator rights, but have no rights to operate the factory at all, and therefore can cause harm to the factory. And third is we see more and more what we call, what we call state actors where we have state-sponsored attacks, every system has to be, or most systems are, in some kind of jurisdiction. There are laws applying to this, and if you operate a distributed system all around the world, you may expose to different jurisdictions and different laws. Laws can change over time, so you as an operator need to be aware of that your system can be affected by changing laws around the world. So we're looking at how can we mitigate such risks to the operators. And there are kind of 4 principles or properties we identified how to protect such systems, or they need to be applied to the systems or to protect them. The first one is you need to be able to separate your critical from non-critical operation or data or code. That helps you to significantly reduce the attack surface if you just filter out what is important for my operation, what data do I need to protect, and run those data in a separate execution environment, what Justus just mentioned, for example, in a trusted execution environment. The second point is the code, what is executed in these environments, in these trusted environments, need to be inspectable by the operator. So the operator need to be able to look at this code, need to be aware of what this code is doing, and also that this code they inspected is the right code which will be deployed at their solution later. The third point is once the code is deployed to the system and is executed, you need to be able to attestate that this code is actually the code you want to execute there and is also executing in the right hardware environment. That is a kind of two pillars that allow you to identify that the code which runs your system is actually trusted and runs in a trusted environment. Every component in the system needs to be able to prove its attestation and also be able to attestate other components it receives or sends data to. The fourth property is to reduce the attack surface, you need to reduce the entities who have access rights or root of trust rights to the solution. In the ideal case, that's the owner or the operator of the solution itself. But every code is running on some kind of hardware, so you also need to have a trust, at least in the chip manufacturer, as you normally don't have access to the design of the chip. So you have the operator as part of the root of trust, as well as the chip manufacturer at least. And the operator then can decide who he actually starts to include in his root of trust chain. So let's have a look at such attack. We actually looked at how Trident functioned on a high level. There were 2 attack vectors, as I mentioned before. The first attack was actually against a SCADA or HMI system. That was the point where the attacker actually was able to operate factory to change parameters there, but was not in a position to actually do physical harm to the factory. In the next step, they actually try to access the system controller itself, change parameters there in order to be able to do physical harm to the factory itself. So these are the 2 attack vectors. I want to dive a little bit deeper how with TCPS we mitigate those attacks to at least these 2 attack vectors there. Let's have a look at the SCADA system or HMI system first. This is systems, this is off the shelf you see everywhere in a factory or on any kind of environment that operates as it operates infrastructure. The first thing, if you recall, you have to separate your code. You have to look at what is critical and what is non-critical for my operation. The critical part, we're putting in a trusted execution environment to separate it from the rest of the host system. In this trusted execution environment, we keep all the secrets that are needed in order to communicate with the rest of the infrastructure. So the certificates to communicate with the rest of the factory line, as well as having a policy decision engine which looks at the command and decides, is this a critical command, is this a less critical command? This is all protected through hardware, through the trusted execution environment. So an attacker to the SCADA system itself will have a very hard time to breach this level of security. As the SCADA system is actually a user input system, we actually don't know if the attacker or the operator actually gives the command. So for that, we introduced a component called the Trusted User Interface. That's actually not a new concept. You probably all have credit cards you use for shopping. If you go to a grocery store and pay, you have the payment system in front of you where all your items are listed on. But when it comes to the critical part of the action, meaning charging your account, this is not done on the big cash register anymore. You have a little, small, secure device in front of you where you put your credit card in, and this is where your amount shows up what you actually pay. And if you look at the amount which is on the big screen and it says $50 and a small device says $500, you probably don't push the pay button because something is wrong. We are applying the same concept to critical infrastructure, to factories, to basically secure and identify attacks against user input devices like SCADA systems or HMI systems. So let's see how this plays out. An attacker somehow gets elevated privileges on the system, can be Linux, can be Windows, some rich operation system, so different attack vectors. He is successful in this attack. He has elevated privileges, as I just said, but the trusted execution environments protects him from reaching further down. So however, he can still issue commands in behalf of the operator to the trusted execution environment. So these commands will penetrate into the trusted execution environment. The decision engine maybe identifies them as normal commands, but when this command reaches the trusted UI, this is comparison again, the credit card that you put into your into the payment terminal. If the operator sees that the secure UI basically requests him to approve a command, he will block this and will identify that this command was not issued by him on the SCADA or HMI system. So this is the first attack. Let's have a look at the second attack, down to the controller which actually controls the factory line itself. So first, I'd like to explain a little bit the architecture changes there again. Again, we have a trusted execution environment. All the critical parts we're moving into this trusted execution environment. So in this case, the example that I will show you here in a minute, we're using OPCOA as a standard industrial protocol. It's an open source, protocol that is used in many factory lines. The unencrypted part of the OPC message handling is moved into the trusted execution environment. From there out, the equipment behind the security gateway which we designed is, let me say, the factory robot or the factory line. This is something which is very hard for you to replace. Imagine it's your $2 million robot. You don't necessarily want to replace the hardware there to put a trusted execution environment there, so we're putting a secure gateway in front of it. And I want to bring your attention to the box which says SPI port IMX6. This line going out there to the blue box, which says SPI LAN adapter with TCP/IP, this actually is a hardware port. This is only connected to the trusted execution environment. That's a feature in the IMX6 which we're using here, which allows us to hide this hardware port actually from the main operation system and only make it available to the trusted I/O. Make it only available to the trusted execution environment, or we call trusted I/O. That means that if a command is sent down the line to the factory controller, it has to go through the trusted execution environment. So in an attack case, the attacker, again, gets elevated privileges over the operation system, can do whatever he wants there, but he cannot reach the hardware pins which actually allow him to communicate behind to the factory line to the machines that basically protected through the security gateway. The next level would be he has to breach the trusted execution environment to do this. So with this, I like to actually move over to the demo here and show you how that looks in real life. This is something we showed 2 weeks ago in Hanover at the Hanover Industrial Fair. I just came back. Got a lot of good feedback there. So let me just walk you pretty quick over here what you see here. Down here, it's our factory. We're just simulating some heat control. Industrial controller you see in many factory lines. Up here is our SCADA system to control the factory. And here are these two additional components that you saw. This is the secure UI, and that is the security gateway. So normally, I have a laptop here to show an attack against the SCADA system and against the gateway. For some reason, I couldn't set it up right now. But you're all developers, so you can only imagine what you can do. If somebody has elevated privileges on the SCADA system, whatever I do here, an attacker could do as well, can basically send commands down. And as I moved the slider, you saw the command was immediately accepted, was sent down to the factory. This is my policy decision engine. Basically looked at this, say, this is a normal command. It could be from an attacker, it could be from the operator, but it doesn't do harm to my factory. It's an annoyance, it can cost financial damage, but it does not hurt the factory or human lives. So I let the command go. If I move this slider up into a critical part, which an operator may is allowed to do, but only for a short time can potentially hurt the factory, you see that the security, the secure UI shows me the command that I'm about to approve. So if I don't approve this command, it will just time out and will not send the command down to the PLC, which then controls the factory. However, I can, if I'm an operator and say, yes, it's a command which is a command that I issued, then I can approve this command with my fingerprint. And you will see that the SCADA UI in a moment will actually adapt to the higher system. And now I'm actually, let me say, control the factory a little bit on a critical limit, which could potentially harm the factory, but it might be still OK. Let me just move this down. The blinking stops. Not this far. You can see we never did this in such a warm environment here. So now let's look at the gateway. So that was the security gateway, which we put in front of the PLC. So any command going to the PLC has to go through this gateway. There are a lot of security gateways out there, but the one differentiator that we saw in the picture before was that the LAN port, which actually connects to the PLC, is coming out of the trusted execution environment. So if I am attacker and I am attacked the gateway here, I get elevated privileges on Linux or Windows or whatever runs on there. I can put any kind of code on there, but I cannot penetrate down to the trusted execution environment and therefore cannot send commands down to the PLC. So as you can see, there's an additional LAN port we put into this gateway. That is the LAN port which actually connects to the trusted execution environment. So with this, let me go back to my presentation. I believe it's this one here. Yep. So this was all pretty much local on the on-site security. But when it comes to systems, especially when we look at a distributed system, we also have the cloud involved there. As I mentioned, there's always also the threat of what we call third-party rogue administrators. Just because somebody else has control or host systems, as can be your system integrator, your cloud hoster, and that applies to everybody there. We also have to look at how can we provide a trusted execution environment in the cloud. And last year, Microsoft announced Azure Confidential Computing, which is basically a secure enclave in the cloud. We're looking into moving some of the configuration and provisioning services which are needed in order to set up trusted execution environments and allow this trusted control of your infrastructure, moving those into Azure Confidential Computing. As the picture shows there, the policy decision engine will be the point of entry again, which decides which data and commands need to go into the secure enclave environment and which data and control can go in the regular cloud environment. Okay, if you want to learn more about TCPS, here are some links, some information we have. We have our white paper. There's a blog post which we did when we announced this 2 weeks ago at Hanover Fair, as well as a quick overview. We are working right now on a preview for this solution. We will send announcements out through those channels there. So let's switch gear a little bit, because I'm in the Windows IoT team. So I want to talk a little bit about Windows IoT security as well. The security promise that we want to give to our customers is that Windows IoT will protect your data at rest, in motion, as well as we just described with TCPS, doing execution as well, where we heavily rely on trusted execution environments. We want to make sure that security doesn't get in the way of your development, deployment. So we want to make it easy for you to use Windows and be assured that the device will be secure, whatever you build there. So how do we do this? We break this down into kind of 3 pillars in protect, detect, and remediate. In the first pillar, protecting, that's where we look, how can we help you to secure your data on your device? How we can help you to build a secure device? And most of the features are probably very well known there for you. We support secure boot. Justus talked about this as well. We're using TPM. It's deeply integrated in our infrastructure to keep your keys secure. And this also includes the keys which help you to communicate to the Azure cloud. We use BitLocker, the same as you have on your tablet or desktop to keep your drive secure. We heavily also using a feature called Device Guard that basically protects you from any unauthorized execution of code. Helps you basically to lock your device down to only the functionalities that are needed for your device. And last but not least, we provide regular security updates to keep your device up to date there. The next pillar I just talked about, trusted execution control. That's all of our efforts, what we do with TCPS. Moving over to detect, we have several services in place, which are mainly deployed right now in the desktop and server side. We're looking into moving those into IoT as well. Device health attestation is already available. Helps to identify if your device is in a healthy state, is it allowed to communicate with services in the cloud or with other devices, to have a trust over the health status of a device. We're looking into moving Windows Defender also to IoT to have a detection of intrusion or any anomalies that may be security related. Will come probably a bit later down the time. To remediate, we have several tools available to do device management, update management. We're also looking into what we call a cyber resiliency or root of trust resiliency. What that means is if your device is affected by malware, a remote device, you're losing control over the device, you cannot reset it because it's somewhere on the outside of a high skyscraper. How do I get back the control of my device? So we're looking into solutions where a device can itself put back into a state where it will communicate again with the owner of the device, with the service, and can basically start fresh over if it got affected by malware, and this malware prevents any communication or any update that would help to get it out of a state where it doesn't operate correctly. So with this, I will give back to Justus.
Hello? 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 Can you hear me? Yeah. Oh, okay, thank you. Thank you, Thorsten. Thank you very much. So the roadblocks to IoT deployment, a lot of it is technical. And for these technical roadblocks, we've seen how Microsoft is doing a lot of investments in the cloud, doing investments to assist people making device decisions, to make the right decisions in order to eliminate these roadblocks. But some of these roadblocks are non-technical in nature. So Microsoft is making IoT a reality to many customers around there in the world. And a lot of times they follow this common pattern where they do a proof of concept for the IoT, and then they'll do a pilot from the pilot to the production deployment, there is always that hesitation, that resistance. And that is important for us, especially developers, because you spend time, you develop a lot of knowledge, you develop this cool application. If that application ends up in a perpetual pilot, you never get it out to production. So that is why this is also important to us, to make sure that we are going from pilot to production. So when this happens, what is the hesitation? At some point, when you've done the technology piece of it, somebody has to make a decision that, yes, this is the time to go into production. Somebody in the executive suite. So the typical questions that they ask is my infrastructure developed, deployed, and operated adequately? So they are asking, what kind of exposure are they going to be bringing to their deployment, to their infrastructure? Remember, some of these are infrastructures that have operated outside of cloud for many years, for decades. Now they are transitioning from a non-cloud deployment to a cloud deployment. So these are huge questions, and these are some of the huge stumbling blocks. So what are we doing to help here? A lot of it comes from education, and Microsoft is doing a lot, bringing together experiences, doing a lot of research in order to avail information in terms of white papers, in terms of webinars and all of that, educating the general public, the people making these decisions, to help them with it. So to begin with, they have to consider what is a threat to them, what is important to them, and what happens if a breach happens in any of those. So they have to follow a formal way of assessing risk in here. They have to understand what threats are important to them and what the consequences of those threats are in order to quantify it. And then secondly, they have to come up with a formal way of modeling the threat. So once you identify the threat, you need to model it. That way you can know how to go about protecting it. So formal modeling methods. And sometimes we give them information, we shared experiences on how they could build in this evaluation process into their IoT project life cycle. So at different stages of the life cycle, there are different things that they need to do. They don't have to wait until the end. Usually that's a very bad recipe. If you wait till the end, you end up with a bolt-on security, which ends up not being optimal. So we'll give information on that. And then finally, some of these things require technical expertise. Sometimes the biggest problem is knowing who to hire for this. Who can you bring in to evaluate with this? So something that Microsoft has been doing is a security program for Azure IoT. And this is bringing together partners, security experts in different aspects of IoT. Some go from end to end. Some have very specific concentrations, like a network security or device security, or the different concentrations. You have partners with a wide span of experience and expertise, with a big breadth of expertise. So these are available. What we are doing here is bring them together and have them as a one-point shop to find the right evaluator or the right partner to work with you. So it will help. What they do, it will help in identifying and then quantifying the risks, and then foster the right decisions towards deployment, and then unblock that perpetual pilot stage so that they can go into production. Okay. A comment about standards in IoT. So IoT is relatively new as far as technology goes. There are deep, rich standards in IT, and there are deep, rich standards in OT. IoT is still this new gray area where the industry is waking up and identify. They know that they need standards on there, but the standards are still developing, as we talked about. So today, we talked about a trusted execution environment. This is something that knowledge has existed in the financial and mobile industry, but not necessarily in the factory or critical systems. So Microsoft is co-chairing a standard organization, an IETF standard work group, in order to help standardize how the provision is a working group called TEEP, Trusted Execution Environment Provisioning, how you provision that. So in general, Microsoft is involved in very many standards organizations trying to drive thought leadership, bringing in experience from customers, driving thought leadership, driving to come up with a way to facilitate adoption, not adoption, but facilitate deployment of IoT to minimize all the fears. So information is key here. and standardization is the way to share this information. One of the recent achievements is the security maturity model from IIC. And this working group is co-chaired by Microsoft to develop a way to formally address how, in a corporate setting, to address the governance, enablement, and hardening of security strategy on there, to have a formal way of identifying what the threats are, making gap analysis, bring in strategies on how to cover those gaps, and then bring in hardening procedures in order to harden that. So if they do this formally, the end result of that is well-documented security procedures, which today does not exist in IoT. So security maturity model is the first one of them, and they released a white paper. They've been working on it for about a couple of years now. They released a white paper, and the standard itself is going to be available sometime in this summer. Okay, we want to finish up with just a couple of comments here. The right mindset in getting it right for IoT. So the first one, you might have heard it in different contexts, or maybe even in this context, that security is a journey, and it is very true here. So a lot of the conversation today will focus on device security because Microsoft is doing a lot of investments in the cloud. But when it comes to device security, a common trap that people fall into is to go, okay, which secure hardware do I want to use in order to build my device? And that conversation may go through how much does it cost, and then decide, okay, yes, this is the hardware that I need, and then from there, they then build a device and then try to build a security story around it. Typically, that is not an optimal path. An optimal path is to start by assessing the risk. What is important to you? What is important to your deployment? What are the risks that you are concerned with? Those risks are then going to drive the right architectural decision, in deciding which hardware, how do you want to secure the device, what kind of secure devices do you want on there. And that in itself will also drive the decision on what operating system strategy, and that goes all the way to deployment and retirement at the end. By the time you go through this cycle, through this procedure, by the end of that, it would be maybe a few years into it, which means the threat landscape might have changed. So you go right back. So it may be 2 years, it may be 4 years, it depends on the industry. But you think of it as a journey. This sense is what makes companies that have excelled or succeeded in securing in different verticals. That is a mindset that keeps them going. So that's the first comment. And then the second comment is very particular to IoT, that success in security in IoT is an ecosystem play. Everybody has to play their part. It's a shared responsibility. If one portion of the ecosystem is failing in security, that ecosystem will not thrive. So it is an ecosystem play, and it becomes very important to identify the different responsibilities and the different roles and self-enforce each other in how to deploy that. So the way we've been approaching it is to try to identify the different benefits for the different roles on there. Today we talked about security promises. So the OEM now knows that, hey, if I do this promise now and I have access to these kinds of markets. The system integrator says, if I use this security promise, now I can carefully balance where I spend my security investment. Should it be on devices? Should it be on operators? So those kinds of decisions, positive self-reinforcement. So that is the information we have for you today. And I just want to remind you again about Azure Sphere, which shows how from all the principles, the 7 principles of highly secure devices, how it's been put together and driven from the silicon through a secure operating system to cloud services. There is a talk on all of that that is going to happen this afternoon. And following that, if we succeed in our security story, our goal is that you as a developer, you develop on a secure system without having to know the nuances or the intricacies of security. And this afternoon, later on this afternoon, one of our teams is going to be talking about a solution accelerator. Hopefully the security principles flow through it, how you accelerate your solution. And the thing that you need to know is that the solution is secured from the ground up, even though they will not be talking about security per se, but it's secured from the ground up because all of this is built into the platform. So we have, despite the list, we have about 5 more minutes, and we'll be happy to take questions. Yes, could you join us, please?
Most of the critical infrastructure attacks, such as Stuxnet and Triton, are not against the software and the devices themselves, but rather in the configured logic blocks that are sent to the devices. Are we looking at IoT Hub integrating with technologies such as blockchain to give us a higher degree of security of configuration going down to the devices, along with a more standardized non-refutable logging of activities going to the device?
Hello? Oh, moment. Okay, now one. Yes, it's actually a pretty good question. In the slides, especially when it comes to logging, we're looking at such technologies like blockchain to basically keep the record true. Implementing such technologies there, yeah, it's one of the goals.
But it's not just logging. For example, you could set up rules within that multiple stations or multiple nodes within your IoT hub have to approve the transfer, and that would then indicate that you would have to compromise more than one station.
Yeah. So that will be part of what we just described as a block, as the a policy decision engine. So that will be integrated in this environment where basically the systems have to approve with each other that certain actions are allowed and can be executed. We are not defining what exact technology to be used, but those blocks and components need to exist and fulfill the 4 pillars that we described in order to create create a trusted solution.
Am I on mic? Can you hear me? Okay, I just want to add to that. At this conference, we also had a talk on device management, which is a new service that we're bringing as well. And it's really meant to address that, the problem of manageability, because security has to be managed. So identifying the devices, having deep visibility into the devices, but a big part of that is working on making sure that the device configuration is what is expected from end to end. So visibility and enforcement. Part of that enforcement is going to require a way to assure integrity on the device side, which is where we're working with the secure chips, the secure silicon, and partnerships in order to build that story. So yes, it is a very deep topic, and we're working towards that, yes. Thank you.
Sort of on the same topic, I guess, with device twins, is there a concept of auditing on that so that so it can be seen when you've made a configuration change from inside the cloud versus it just happening?
So if I get the question well, like in terms of notifications?
No, just sort of like a history and auditing capability in device twins, so it's possible to see what changes have been made and by whom.
Oh, absolutely, absolutely. So the device twin is available to all the Azure services that you can build. You can build and automate how you want to do that. You can query devices. You can tag devices that you're interested in. You can tag them accordingly, build jobs around them, and do automated queries or automated aggregation of notifications based on what is interesting for you.
Yeah, right. But is there an audit path for that? So I can go back and see what changes have been made and when?
I'm not an expert on that, but that's something that we could give you the information on that, yeah. Okay, any more questions?
Yeah, I got another one. Azure Sphere question. Assume that the original, like the early builds of Sphere will have trusted element but not trusted enclave, is that correct?
So I didn't catch the question.
Yeah, me neither.
The early versions of Azure Sphere, will they have trusted element? They must have it, right?
Oh, for Azure Sphere.
Yeah.
Oh,
I really encourage everybody to go there for the details, but they have enclave as well.
They have enclave as well. Okay,
yes.
Thanks.
Yes.
Any more questions?
Any more questions? Okay, thank you everyone for coming in. We very much appreciate you being here. Thank you.
Oh, thank you too.